I'm Aditya Kanade and I am going to talk about attention guided deep learning framework for movement quality assessment. We start by looking at the challenge faced by patients undergoing at home physical rehabilitation. Around 90% of all physical rehabilitation programs are home based. Home based programs usually have a set of prescribed exercises which the patient needs to perform for recovering from an injury. These programs are usually very long in nature, and thus constant supervision by a clinician or a physiotherapist is not possible due to economical constraints. Thus, patients either have to self-monitor or take help from their family members to assess their performance. The literature of movement quality assessment has tried to bring in a technological intervention to this problem. In this work, we identify research gaps in existing literature and propose a new deep learning framework to address these problems. This is the outline of the presentation. We begin by looking at the existing literature and identify research gaps. Based on this information, we present the proposed architecture of a deep learning model which tries to address these issues. Next, we compare the proposed architecture with existing state-of-the-art methods. Further, we see a computational cost analysis between existing methods and the proposed method. Next, we look into the attention maps, which are a step towards improving interpretability of the predicted assessment scores. Finally, we end up by summarizing the contributions of this work and some future research directions. Figure 1 shows the flowchart of a typical at-home rehabilitation system. The patient performs an exercise from their prescribed set. Their motion is recorded by a mocap device such as Kinect or Vicon. These devices usually track a few important key points of the human body and provide joint orientation and position data at each frame. Once the patient finishes their performance, the data collected on mocap device is passed to a processing unit which compares this performance with a database of pre-recorded performances and rates the performance, thus giving the patient the movement quality assessment at their home in an unbiased manner. Figure 2 shows the data collected on the Vicon mocap system for an exercise. Initially, methods for movement quality assessment were capable of only binary assessment, where they could only identify whether a performance was correct or not. However, it would be a long time till a patient sees their performance falling in the good category in such systems. This can be highly demotivating. Thus, this called for more fine granular assessment methods. Recently, methods based on spatiotemporal CNN and graph convolution network have been proposed for assessing movement quality. These methods are either slow to train or lack interpretability of the predicted assessment score. It is important to note that interpretability is crucial for deep learning models because it allows us to understand how the model works, what factors it considers important, and why it makes certain predictions or decisions. This understanding is necessary to ensure that the model is making accurate and fair decisions and to identify potential biases or errors in the model. NN models, neural network models in existing literature use RNNs as a major building block. RNNs are prone to slower training times. Thus, we have chosen the transformer architecture to allow for faster training time. However, transformer operates on tokens, which calls for tokenizing the movement data, which is of continuous form. We begin by slicing the movement data collected over the exercise duration into small temporal windows. These windows are passed through an embedding layer, which projects the input to a lower dimensional space, making it easy for the transformer to operate on. Furthermore, these feature vectors are appended with the positional embeddings to keep the temporal coherency. The set of these features are passed to the base of the transformer encoder, which extracts rich information. The features at the top of the transformer encoder are passed to a stack of MLP layers, which outputs the regression score. The training objective is to minimize the difference between the predicted assessment score by the model and the ground truth score. We now discuss the embedding layer in detail. The embedding layer in the proposed architecture splits the human body into 5 subgroups. Each subgroup Data for each subgroup is processed independently through a multi-branch convolutional block. The extracted features are then passed through the multi-head attention block, which selects the feature from specific subgroups important for accurate score prediction. Thus, an evaluation of the attention map can lead us to interpretable assessment score. From table 1, we now look at the benchmark results of the proposed method. From table 1, we see that the proposed method performs at par with the existing state-of-the-art methods on the clean Vicon data. However, the proposed method outperforms other methods on much noisier data collected from the Kinect system. It is important to note that a system like Vicon is impractical to be set up at home due to associated high costs. However, Kinect-based systems have been increasingly becoming cheaper, thus making it more suitable for home-based applications. We now look at the computational cost analysis of the proposed method. It is clear from the table that the performance improvement of the proposed model is coupled with lower training and inference time. This is an important metric when developing systems for home-based settings where devices might not be powerful. The attention score map figure shows attention maps from multiple heads of the embedding layer. Even though the model was not trained to associate usage of a specific body part with the ground truth score, attention map shows how the network is able to come up with these relationships. In figure, we see that the patient is performing a standing shoulder abduction, which is an upper limb exercise, and by observing the attention maps closely, we see that the network is indeed paying attention to the upper limbs and trunk for predicting the assessment score. We believe that this is just a start towards bringing interpretability of the assessment score, and that our work will motivate research community to address this issue with newer ways. To recap this talk, we saw a novel attention-guided deep learning framework which assesses home-based exercise performances. We also saw how the attention mechanism can be leveraged for making the neural network model more interpretable. We also saw how doing away with the RNNs, that is the recursive neural networks, and replacing it with the transformer architecture drastically reduces the training time. On an ending note, the current network still learns to align the predicted score with the ground truth score, and it still might not learn correct relationship between the usage of specific body areas to a particular score. Once such a relationship is established, the bigger question on why, that is why a lower score or why a higher score, can be addressed by the model itself, thus bringing in explainability of the assessment score and bringing such a system very close to a physiotherapist or a clinician who might observe the patient performing. These are the references for this talk. Thank you.